In this video, we're going to continue our discussion of matter. And like we said in the last video, matter is basically anything that has mass and takes up space. And generally, when we think about our world, everything we see and feel and interact with in our world is made out of matter. Now, in trying to classify matter, we can go back to the Greeks and have our first recorded attempt to describe the world in terms of elements. And their description of the elements were basically earth, wind, fire, and water. And while it was a decent attempt to try and explain the world based on the technology they had at the time, we now know that these are really just phases. We have the solid phase, earth, the liquid phase, water, the gas phase, wind, and energy as the fourth type, which would have been fire. So in describing the world, we can trace two Greek philosophers and their attempts to describe the world in which they lived in. And the two philosophers were both Plato and Democritus. Plato was more of a philosopher of thought, whereas Democritus was more what we would consider a scientist. He was a natural philosopher, so he focused his efforts on trying to describe the world based on observation. And Democritus posed a question that, can you take a material, something like a piece of paper, and divide it to the point where it no longer has the properties of being paper? So at some point, you get to a certain size particle that if you were to cleave it, divide it, rip it in half, or otherwise alter it, it would no longer be the same particle. It would be something else. And that is what essentially the atom is. It is a particle which is unique compared to other particles. It has some definite characteristics in which we'll talk about in a little bit, but you can't get smaller than the atom. Now, Democritus almost got lost to history because Plato was an avid rival of Democritus, and Plato basically outlived Democritus. They lived around the same time, but Plato lived a little bit longer. And in an attempt to remove Democritus's efforts and contributions to philosophy, Plato basically had all of Democritus's works destroyed, except for a few pieces which survived. So that's how we know Democritus was really the first attempt to classify the world around him. Now, when we talk about atoms, the model of the atom has undergone a number of iterations. And the simplest iteration was that the atom was just a solid sphere that was unique. Essentially, it was a Lego. And for a long time, that was the prevailing theory. And during the course of about 100 years, that model of the solid sphere was completely shaken up and underwent a number of different iterations. So going from a sphere to a plum pudding model, which basically advanced the story of the atom, saying that, no, it's not just a neutral solid sphere. It's actually a particle that has positive and negative charges in it. We would go to the nuclear model, which says that there are positive and negative charges in the atom, but the negative charges aren't actually in the same location as the positive charge. We had a very briefly lived planetary model, which we can just ignore for this class. And then we have the quantum model, which is the mathematical description we use for atoms. So how did we go from a solid sphere to charged particles? Well, there were a number of different experiments which actually teased out the structure of the atom. And so we have the three subatomic particles of an atom, the electron, the proton, and the neutron, which were proven to exist experimentally. So we'll talk about the electron first. The electron was first observed by J.J. Thomson and then later confirmed by Robert Millikan. And what J.J. Thomson did was he took a cathode ray tube, which is basically what we used for old-fashioned televisions to get them to work. And he would have two plates here. And these two plates, one would be negatively charged, the other one's positively charged. And he would conduct current into the negative one. So what would happen is the negatively charged electrons on this plate would get excited, and they would jump off it and move towards the positive plate. Well, in the positive plate, there was a little hole in the center. So what we got was a nice beam of electrons. And so because there was a hole in the center, this beam of electrons would actually go through the plate, where it would encounter two metal plates that had an electrical charge on it, so a positive side and a negative side. And what J.J. Thomson found was, as he changed the magnitude of the positive and negative side, he could get this electron beam to sweep and move around. And from that, he could determine that this beam was full of negative charges. And so he knew there were negative charges, and he could work out a ratio of mass to charge, but he couldn't actually figure out what the actual charge of these electrons were. Well, this experiment was followed up by Robert Millikan, who did what's known as the oil drop experiment around 1919. And what Millikan did was figure out the charge of an electron by taking some oil droplets here and spraying them into a sealed canister which had a vacuum in it, so there weren't any other particles other than the oil drops. And these oil drops would slowly go down towards the bottom. So he had a plate here with a small hole again, so only a few of those oil drops made it through. But when they passed through this plate's hole, again, he would induce a charge on it, so that when they fell down into the rest of the container, they would pick up a charge. They would have a negative charge on them. And what he found was these oil drops would hover at very specific increments. There was either an oil drop at a particular height or there wasn't. And so he had essentially these different levels of oil droplets. And from those different levels, he determined the charge of an electron as well as the mass of an electron. So what we got out of these two experiments was confirmation that the electron was a negatively charged particle. It was incredibly small in mass. In fact, the mass of an electron is so small, we don't even really consider it other than in nuclear chemistry. So all calculations we do, we basically just ignore the mass of an electron because it's so insignificant compared to the mass of a proton or a neutron. It's like worrying about having $1 million and whether or not you have 10 cents in your bank account. If you got $1 million, you're probably not worried about that 10 cents, so you essentially ignore it. We also found that electrons reside outside of the nucleus of the atom. And the nucleus of the atom is what we'll talk about next, but basically the nucleus is where all the tangible and significant mass is. We also know that electrons are constantly moving around the nucleus, so they are in constant motion. They're not static. And one thing we'll learn about later on in the course is that it's impossible to know both the speed and the position of an electron simultaneously. The more we know about one, the less we know about the other. And unfortunately, that seems to be the case until someone can prove otherwise. The next experiment was known as the Rutherford gold foil experiment. And the gold foil experiment had a piece of gold foil sitting in the middle of this coil of material that was sensitive to radiation. And what happened was we would shine alpha particles, or basically helium nuclei, the result of nuclear decay. We would shine this beam of particles at the gold foil. And the original thought was, if the atom was just a solid sphere, then this beam of particles would basically bounce back towards the source of the alpha particles. And what we saw was, remarkably, that that beam almost completely made it through the gold foil. We also found that this beam was deflected in all sorts of directions, including back towards the alpha radiation source. And what this meant was that really the mass of the atom is incredibly small, and that the atom itself is mostly empty space. There's a very small location where all the mass lies, and if the alpha particle, or the alpha particle hits that spot, the nucleus, then it bounces back. Otherwise, it just goes through and by virtue of the nature of an alpha particle, it can be deflected when it comes near an electron. And so that is how we learn that most of the atom is just empty space, but there is a small space called the nucleus, which is full of the mass. Now, protons are one particle that are found in the nucleus, and protons have a mass and a charge which is positive. So we've got electrons with negative charge, we have protons with positive charge. And the amount of charge a proton has is simply equal to that of an electron. It just has an opposite sign. So we say protons are positive and electrons are negative. And so when we have a neutral atom, we have equal number of protons and electrons. Now, the proton is what defines an element. It defines the element's identity. And so when you look at the periodic table, you will see each element has a specific number of protons. So all helium atoms have 2 protons, all hydrogen atoms have 1, all iron atoms have 26, and so on and so forth. So if you change the number of protons, you change the identity of the element. And if you're changing the number of protons, you're doing nuclear chemistry and not the traditional chemistry we talk about in a freshman class. So the last particle that was discovered was the neutron. And the neutron was suspected for a long time, but very hard to prove, because protons and electrons have charges. That means that we can manipulate them using magnetic fields. The neutron is a particle with about the same mass as a proton, but has no charge. Its function in the atom is to act like glue. It keeps the protons close together, and it prevents them from flying apart, because when you have like charges next to each other, their tendency is to repel and get as far away from each other as possible. But when you have neutrons present, they act as a type of glue that helps keep all that positive charge in the nucleus. Now, a proton defines an element's identity. And so every atom has a very specific number of protons in it. However, that's not the case with neutrons. Each element can have a different number of neutrons. So when you have elements with the same number of protons and different number of neutrons, you have what's known as an isotope. And isotopes are incredibly useful tools we use to explore our past. We can look at isotope ratios of different elements and infer how old something is, for example. So our view of the atom is that it's the smallest stable form of matter in the universe. Every atom has a proton, they have an electron, and all but hydrogen has a neutron. Hydrogen's the only element out there that doesn't have a neutron, although some of its isotopes do. But most hydrogen atoms are just a proton and an electron. Everything else is a proton, neutron, and an electron. So in terms of how big and small the atom is compared to the nucleus, we're talking about an atom being on the order of 1 to 5 angstroms, which is about 0.1 nanometers, 0.1 to 0.5 nanometers, or 1 to 5 angstroms. Of this space, of this volume, the nucleus is 10 to the negative 4th angstroms, so it's 10,000 times smaller than the size of the actual electrons which surround it. It's like comparing the size of a baseball in the middle of Phoenix to the outermost edges of the suburbs. It's really small, to give you kind of a crude idea of just how much empty space there is in an atom. So I'll leave you with this slide, just kind of summarizing the subatomic particles and everything we've discussed. You don't have to memorize the atomic mass of a proton or a neutron. You should just know that they're about the same. Neutron's a little more massive, but that's it. So we'll see you in the next video.